the following problem consists of introducing our model of cognition, referred to as MOM, or model of models, to be potentially used for constructing an AGI. Then we elaborate about three aspects of cognition in our model, which are will, planning, and understanding. Next, we dive into how knowledge can be represented to implement these three aspects of cognition. Finally, we will see some examples. For starters, ChatGPT is, in our opinion, a first version of AGI. Even though it's a bit lame version of it, but it's still an AGI, because it does perform quite well in many tasks. Hence, GPT is a general purpose model, and it generalizes to some extent to new tasks. However, it hallucinates with confidence and do not perform well in reasoning tasks that requires logic and step-by-step thinking. One of the reasons for this is that masking or next word prediction is not enough as a prior knowledge to align with humans. Also, GPT has no world model. It's simply mimicking text or images like Midjourney. In our opinion, this prior should integrate different brains' cognitive capabilities or functions. Therefore, we propose a neurosymbolic hybrid cognitive model, where the ideal and mature state of the AI is mainly symbolic, while the evolution process required to reach this state is accomplished via deep learning. This presentation is about this ideal final state of cognition, or the goal state of an adult artificial intelligence. Our basic assumption and principle is that cognition is about operating on accumulated knowledge with the guidance of an appropriate will. The purpose of this presentation is to convince you it is a good enough assumption to build an AGI prototype. Again, please note that the current proposal is not yet implementable nor practical, but simple cognitive representation or model, meaning how thinking works, how knowledge is represented, but not how it is learned or other optimization process. This will be addressed in the evolution part in the future. One general evolutional scheme is proposed at the end of this presentation. First, we'll start from will, and we'll ask ourselves why will is needed in cognition at all, because cognition is mainly about logic, isn't it? No, it's not only about logic. We attach will to most of the interactions we have in the world. For example, when we encounter an object, we try to evaluate its function, its potential use for some purpose. Similarly, we try to figure out an animal's inner state so that we would know how to anticipate and understand its behavior. We also assume some will behind people's actions and behavior. And finally, we contemplate about life's biggest mysteries. Maybe because will is rooted so fundamentally in us. This brings us to the belief that a full model of any entity consists both of knowledge about it and about some will associated to it. We can see many examples for this idea, especially at math classes, where the student don't comprehend the material he learns deeply, though he can certainly absorb only the shallow view of it. Either it is a simple memorization or a technical understanding of the material, such as not understanding the meaning of stuff but only their utilization, meaning technical understanding. In other words, just to know how a method or some formula can be used, without deep and full understanding of the concepts, such as determinant in algebra or Green's theorem in calculus. These are all examples of partial model. Next aspect of cognition is planning. Planning starts from will in the form of a vector field, similar to any physical field such as electrical one. And just as electrical field, we have two types of will: to get away from something or to get to something, or both. In either way, we get a will field. Next, we'll see how each of these three cases evolve in time. We start from some problematic situation. Our will is to move away from it. At first, any place outside the problem state is preferred. But as we refine our will, or figure out more precisely where we want to be, then our goal states shrink to become more specific, and a purpose appears. Next, we'll see the opposite case, where the will is growing from the final state or states, searching the best state to start the full solution from. Final case is when we are given both the problem and the goal, as in any problem-solving test. Now, after the will was refined or defined, how we implement it? We're doing it by adding the knowledge to fit it accordingly. Supposing we have the two realms, the will realm and the knowledge realm. Our goal is to align them. To represent the same space. Now we present some definitions. As the will realm is composed of vectors and knowledge realm is composed of states, we can define the state as the full world or environment information at some time instance, while actions are what changes states, or more precisely what transform one state to the other. This is a typical definition in many science fields such as in classic AI, reinforcement learning and control theory. Eventually will, like action, are both vectors in state space, only we assume that usually will is affecting the preference of which action to be selected to change the current state. Note that the states are discrete while actions can be either continuous or discrete also, and the will is acting like a filter to reduce the amount or the range of possible actions we should apply to change the current state. This allows a more efficient and faster problem solving, since the solution space is reduced significantly. Also note that the state represents only the relevant elements of knowledge, and not everything there is in the world, since we have a limited working memory. Using this alignment, we want to move from the specified will to an actual plan within our knowledge models. After the will was established due to alignment, we can transfer to the knowledge model space. Then a planning can be initiated involving the available models. The first, most intuitive solution that pops up is almost the shortest path from problem to goal. However, it is not considering constraints of the problem and of logic. Hence, for the real solution, we try different paths, either close to the intuitive solution or far from it. Note that this alignment is what makes organization of knowledge or models, which is necessary for effective problem solving instead of blind search. So the AI works hard in organizing and aligning the actions in order to work with minimum effort in the future for fast response. Also note that there are other considerations not presented here, such as confidence, resources, constraints, costs, and other factors that are part of planning. This implementation of will is better explained in 3D layers. We can see three layers, where the top one is will field, then the middle one is a layer of knowledge models, while the bottom one represents the actual details or realization of the proposed solution by the models. If we disregard for a second the will level that directs all the models below, then we can see that the models are also comprised of levels. which are separated by the amount of abstraction or grouping. For example, we can see an abstraction or inheritance of classes and an instance in the reality below them, the cat image in reality, then above it the cat class, then the animal class above it, and then object class above it. The selection of models for solution is made by attention mechanism. For example, we see concentrated attention on a single model, but usually the attention can split. We can view will from above like a bird view, where we can look at it like coarse to fine hierarchy. The highest level is vague, with coarse composite models where nothing is seen clearly about the ground, and as you descend the levels you see more details. Finally, we evaluate the solution in reality. It is an iterative and cyclic process where we can go back and forth, up and down the levels in looking for different solutions. It is like geographical maps with different level of details or resolution. Next aspect of cognition is understanding. While previously we've seen planning working in top-down fashion, or in communication perspective, it is the sender implementing its own will and convert it to a message with words. In understanding, on the other hand, it is a bottom-up process, or in communication, it is the receiver trying to retrieve the sender's original intention or will to comprehend the message authentically as possible. While we have seen so far only the macro view of cognition, the next step is to discuss how the knowledge models are actually represented. We represent each object or class along with its features and actions, or in the equivalent graph view on the right. Remember that all these elements are also classes themselves. We propose also to include a measure of relevance to prioritize differently the elements that belong to the class, to enable more efficient cognitive operations. As we'll see later, it is very important. After the definitions of knowledge basic elements, we can represent a state as group of objects, and actions as those that operate on one or more objects in the state. The actions are learned, and the will is specified usually in the first states. As we showed previously, the will and the knowledge models are aligned, so that the will would be guiding the states to select the most relevant actions. Also, since we use forms, we can aggregate several objects or actions by abstraction or grouping. Next, we see how to utilize the knowledge representation for inference, mainly to fill missing information or common sense knowledge. Given a knowledge map, suppose we perceive an input, which triggers some object in the map. Then an inference process starts to characterize this object by propagating and activating relevant features, either via one step or more. Similarly is with the following triggered objects. But the inference scanning is not blind. It is usually also guided by will, a basic form of will, simple question type of will. This inference occurs not only in understanding but also in planning, specifically to comprehend the problem and the goal. We can use the same illustration from before to demonstrate how creativity can come to play. But we start first from its counter effect, recognition. Recognition is about finding past learned patterns, for example, by picking the most admissible actions or relevant features. Here is an example of an old and tall person walking the long boulevard of New York. On the other hand, creativity is when we allow for some extent to pick the less relevant actions or features. As we see, for example, after imagining an elephant and inferring its features, suddenly imagine an implausible feature of it, flying. Then we need some wings to enable it to fly. So we imagine its ears to act as wings. Thus, we got ourselves Dumbo, the flying elephant cartoon character. In this scenario, we allow for some infeasible paths, but we try to keep the logic. So it's not just random creativity as in Midjourney or DALL-E 2 or other deep learning image generators, but rather it has structure, similar how to human artists perform. Now we'll see examples to visualize and grasp all the ideas we've seen so far. But before we jump in, we should note that we separate language from the actual cognitive operations, since these operations are more fundamental processes than language's specific structure. Hence, in the example we'll see, we disregard language transformation. Also, since the mature state of the knowledge map is assumed to be learned in the evolution phase, the phase that is not presented here, hence the knowledge in the following examples is merely hypothetical demonstration, while in reality it could be different. In this example, the cartoon of a head emphasizes that an attention is split. One part is perceiving incoming information, while the other part is trying to comprehend the total accumulated information received so far. First, it triggers the fish object, then, guided by what question, it extracts the relevant feature. Next, it is ready to use language model to phrase the goal state in a correct grammatical form. This step is avoided as mentioned previously. Here, the dog class is triggered, and then an instance of it, assuming it to be the last discussed dog, is accessed. Again, we use will to extract the relevant feature. Next example is viewed by dynamic representation. As an alternative to a state-by-state static representation we've seen previously. In it, we show that high-order thinking can be expressed as a hierarchy via grouping. Actually, the group can be expressed in the same level. This hierarchy is similar to part-of-speech parsing. The following example presented as a problem-solving task. Also, we see a group object in the problem state and its cause feature. An appropriate will field is induced for this problem. This example also illustrates the hierarchy of objects due to abstraction. This is a short visualization of one proposed solution, displaying only the main elements in each intermediate state. More accurately, this is done via model hierarchy. Another example of such abstract planning is presented here. Here, we show that not all state transitions are deterministic. Many of them are stochastic even for the agent's actions, and many others are stochastic due to dependence on other factors besides the agent. Like in any game, for example chess, we can see, for example, that states are abstract. That is, they have unassigned or unknown class variables. In order not to make this planning too much stochastic, we try to consider only most probable possibilities and disregard planning the response to any of the possibilities. In this example, we derive the states from a story string. Between the inputs, we can see the inference progress. We can also produce past states if it is derived from the story. Another inference. Eventually, this is a mixed example to show that the first step is understanding and the next step is planning. In this case, it is kind of a story completion task. Hence, the next task is to solve the problem or to figure out the how. We do it by decomposing will or actions to reach as most detailed solution as possible, as we have seen in the implementation of the will slides. As can be seen, actions and will are interchangeable. Sometimes we call it will and sometimes it is an action. As mentioned previously, planning is a top-down process. Alternatively, we can view the solution as a story to be understood by some other listener. This evolves as usually as a stream. Only this time, we try to reconstruct the original will from the detailed actions. Hence, it is a bottom-up understanding process. Also note that at each state generation, there is also local inference processes, which can be regarded as internal will, as opposed to the external will, which we try to reconstruct from the story. These two types of will can be categorized as micro and macro. From the previous examples, we can conclude that every change, either in features or due to actions, are always guided by will, or as frequently as possible. More generally, actions as algorithms are represented via flowcharts, where there are many possible scenarios. Here we see an example of some abstract algorithm, as we have seen demo of such algorithm in math problem. Here we can see that besides sequence grouping we have seen so far, mostly in temporal stories, there could be also compositional grouping, or more generally any abstraction. Next, we discuss some special cases. First, we show how actions similar to functions can operate on several arguments, or in our case on several objects. Secondly, we can represent processes throughout several states. Or how new objects added over the states. Or objects that are removed due to the pass of time or forgetfulness. And again, we can see actions that are applied on several objects. If we recall our state space definitions, it is not quite clear how will is derived from state, especially from the first state. As stated previously, will is learned, but this claim is too general. Why? Since in most examples we've seen the will were specified explicitly in the state. Recall the math problem, the robot request, or the simple problems. This is true mostly for inanimate objects, but there are many cases that will is implicit and hidden from us, such as for animals or humans. Again, inanimate objects are very straightforward, but animals are driven by hidden inner emotions. Though humans can also act upon emotions, however, some people acquire second nature that override emotional responses, usually derived from some set of values or beliefs. This set of rules is similar to language rules, acting as an interface between two entities. But any set of rules is also deterministic, and so is the derivation of will from emotions in animals. So how animals and humans models are still stochastic? Indeed, these three mechanisms are deterministic by definition. However, it is not the case for an outside observer or listener. For the animal, it is usually hidden, while for the human there's also a second factor, the free will, struggling between these mechanisms, to choose to behave accordingly to values or not. Finally, all these mechanisms as perceived by an outsider can be modeled in three forms, ranging from totally deterministic, as an if-then rule system, up to totally stochastic. In the following are some examples of these three forms. This one is about an inanimate object. This one is about sensory perception transformed into our knowledge map. This one is about sensory perception, specifically from different modalities. This one illustrates humans' different options to act or react. This one presents a psychological experiment that tried to teach a dog to associate a hearing ring from a bell to being food served. We see that before the experiment, the dog has no special reaction to a ring, but after enough training, we see he has developed a dominant response in the form of drooling, which can be directly translated to its will of expecting a food to be delivered. So what do we actually propose here? In essence, what is presented in this presentation is a cognitive model, or a model describing how thinking works. In this model, we describe how different thinking processes occur, including learning and knowledge representation. Even if it's not how the brain works, it still can be utilized to build an AI agent, like other virtual assistants, ChatGPT or Elise, Alexa, Siri, and others. However, this presentation is only the ideal or the final state of intelligence. The main part that is not presented here is the learning. So our proposal is not implementable yet, not practical, but simple cognitive representation or model. Meaning how thinking works, how knowledge is presented, but not how it is learned. Okay, and what exists so far? From the early days of AI, there are expert systems which are based on classic AI. This is mainly based on logic. Nowadays, there are large language models that are based on machine learning, or more specifically on deep learning. Each of them has advantages and disadvantages. In one relevant aspect to us, they are different: the perception of will and intention throughout communication. The logic-based systems are based almost solely on cold and precise logic. This is mechanical and technical perspective of intelligence. The deep learning models, on the other hand, are usually do learn will and intention from data. However, it is done very implicitly, hence cannot be generalized to any random and flexible conversation. It makes these both approaches lack of common sense and especially of full understanding and comprehension of the situation and of the request from the human user in both directions, both in understanding humans' intent and in replying in human-like logical way. And what is the novelty here? The new thing compared to existing approaches in AI is that we explicitly learn will in the models. The models that we construct in our mind while interacting throughout our lifetime. From inanimate objects like basket and table, through animals, humans, up to abstract theories. This will becomes essential part of any model, and in order for it to be part of our physical reality and affect things, it is aligned with our knowledge. whether it in a logic-based form or embedded in neural networks.
This alignment is useful since it creates intuition between problems and admissible actions. It provides kind of heuristics for solving new problems.
One frequent question about all this model is obviously, can we actually realize all this? Or is it merely a theoretical, unachievable model? So first, it is currently in the process of research. We always have deep learning and machine learning at our disposal. Secondly, even if we discover that the implementation is difficult, it doesn't mean that the model is wrong or that it should be disregarded. All the prior described in it is still valuable, and in our opinion, even essential, to build an AGI that can understand humans and that we can understand it.
Still, there is one proposal, though in very high level. Here it is. This implementation is done by applying different priors in sort of developmental process. We start from recognizing symbolic features. Then we can associate and group these features to characterize objects. This is the what step. Then we learn how to operate on these objects, meaning by actions. And actions are simply algorithms. Then finally, we add directionality to these actions to make them relative to each other and context dependent. This overall process is cyclic, meaning whenever new features learned, new associations to objects occur, new actions can always be added, and directions can be updated.